Welcome, my name is Carlos, and first I want to thank you for showing interest in me and my group. In this video, I will tell you a little bit about who we are and what we do, and let me start by introducing my trajectory. So about a year ago, I became a faculty member of the Wilczek Quantum Center in Shanghai Jiao Tong University, but originally I am from a city called Valencia in Spain, which is home to the most delicious rice that you will ever eat, called paella, and also to one of the craziest festivals that I know, in which we build wood monuments the size of a building and then burn them after 3 days of celebration. So it is at the University of Valencia where I studied theoretical physics, and then I did the PhD under the supervision of these two fantastic human beings. But in addition, I was also fortunate to develop parts of my PhD at the Max Planck Institute in Germany, at Swinburne University in Australia, and at MIT in the US. So funny enough, MIT is home to Frank Wilczek, who is also the chief scientist of my current center. So on the other hand, at the Max Planck Institute, I was supervised by Ignacio Cirac, who is one of the pioneers and most influential figures of my field, and I found his group such an inspiring environment that I went on to do a 4-year postdoc with him. And then after that, I moved to another Max Planck Institute not too far away, first as a postdoc and then as the leader of my own small group. So I don't want to bore you with many details of my CV, which you can find in my webpage, where I give all sorts of details about my physics and my music. And here I just want to summarize the 4 aspects of my career that I am most passionate about. So starting from research, for which I have produced 1 book and over 30 research articles. But I also love teaching, and in particular, I recommend you to check the materials of my quantum optics lectures, soon to be a book, but available for now in my webpage. So I have officially mentored 6 students so far, but also many more unofficially. In particular, writing 16 of my papers with people that I have mentored in one way or another. And finally, my other big passion is music, and in particular guitar, and actually all the music that you are hearing during this presentation is all my music. And if you are curious about it, you can find all the details in my webpage as well. Okay, but enough about me. Let me now introduce my group on open and non-equilibrium quantum optical systems. So we are part of the Wilczek Quantum Center that you just saw in the small music clip that I showed, and which is a unit of the School of Physics and Astronomy at Shanghai Jiao Tong University. So at the moment, the group has 2 postdocs, one from China and one from Iran. There is one Belgian full-time PhD student and one Pakistani PhD visitor. And I also work with very talented students from Germany and from China. So as you see, we have a very diverse group, not only in terms of nationalities and cultural backgrounds, but also in terms of scientific topics. So many of these topics come from my own interests, but I am also very happy when people bring their own ideas and even external collaborations. And well, talking about research topics, let me now explain you in more detail some of the research that we perform. field is theoretical quantum optics, a subject whose traditional scope has been the description of light-matter interactions. So as a characteristic system, you may think of the light inside an optical cavity interacting with some matter made out of atoms. However, in my opinion, this definition is very narrow, as the most characteristic feature of modern theoretical quantum optics is not the specific systems it applies to, but rather the type of situations that it describes. For example, typically, cavity mirrors are not perfectly reflecting, and then we can introduce energy into the system, but energy also leaks out of the system. Therefore, for me, the most characteristic feature of quantum optics is that it deals with quantum systems that are open, meaning that they interact with their environments, and they are also driven out of equilibrium by external means. Moreover, the type of systems that quantum optical tools are applied to are extremely diverse nowadays. For example, let me show you the ones I have worked with the most, that go from light interacting with atoms, ions, or the electric materials, to far more exotic platforms such as circuits made out of superconducting materials, or even the quantum motion of large objects. Therefore, in my opinion, a more accurate description of modern quantum optics would be as the field that studies systems described by quantum electrodynamics at low energies under open and non-equilibrium conditions. So this means that quantum optics has grown into a very multidisciplinary subject that works in full synergy with other fields, especially with quantum information and quantum technologies and with condensed matter physics. So related to these fields, let me mention a few topics that we have put some efforts on. For example, the quantum properties of light and the manipulation of atomic systems, quantum sensing and communication, or the transition from the microscopic quantum world to the macroscopic classical one, or phase transitions and many-body theory. But the topics that I find even more exciting are the ones that spill from one field to another. For example, quantum optics provides experimental platforms with which we do quantum information, but at the same time, quantum information provides the conceptual tools that we use to characterize states in quantum optics. Similarly, quantum optical platforms allow for the simulation of condensed matter models, even in regimes that cannot be studied in real materials, but at the same time, ideas of phase transitions in equilibrium are borrowed from condensed matter to define similar concepts in the open systems treated in quantum optics. And along this direction, perhaps I can give you more details about one of our latest research directions, which is related to the so-called bosonic typebinding models, which are essentially the class of many-body problems that are somehow closer to traditional quantum optics. So let me explain what this means in detail. So first, typebinding refers to the fact that there is some notion of spatial dimensionality underlying the model. For example, in the form of a lattice like this one, where only nearby sites are connected, generating a two-dimensional structure. On the other hand, bosonic refers to the fact that on each lattice site, we define a harmonic oscillator leading to a set of annihilation and creation operators that satisfy canonical commutation relations that I'm sure you all know. So perhaps the best known model of this kind is the so-called Bose-Hubbard model, which is formed of a Hamiltonian containing a kinetic term in the form of excitations that can jump between neighboring sites, and a potential term or interacting term that provides an energy penalty whenever two or more excitations coincide at the same lattice site. So when interactions dominate over hopping, the eigenstates of this Hamiltonian are just the Fock states defined on each lattice site separately, and therefore the system behaves as an insulator. That is, if we add an excitation at one edge of the lattice, it will not propagate. In contrast, when the kinetic term dominates, the eigenstates become delocalized because now an excitation created on one side of the lattice can propagate via tunneling, and the system becomes now conducting, or in the context of indistinguishable bosonic particles, we call it superfluid. So it is by now well established that these two phases are connected in a non-analytic fashion, and therefore the Bose-Hubbard model is the simplest one that presents a quantum many-body phase transition. So this model can be implemented in the laboratory with atoms cooled down to extremely low temperatures and trapped by a potential generated by the standing wave associated to counter-propagating lasers. So as you see, this would be a simulation of a condensed matter problem with a quantum optical system. So the point is that here atoms can tunnel to neighboring sites of the standing wave, and this is described by the kinetic term of the Hamiltonian, and on the other hand, when they meet at the same lattice site, they can scatter, so literally collide, and this leads to the interaction part of the Hamiltonian. So this was an absolute revolution 20 years ago when it was first proposed theoretically and implemented experimentally. But nowadays, we are starting to implement the model with more modern platforms. For example, with superconducting circuits. So you all know that an LC circuit behaves like a harmonic oscillator, but what is very surprising is that actually, if we make it resistance-free and cool it down to low enough temperatures, so the current becomes decoupled from any environment, it behaves actually as a quantum mechanical harmonic oscillator. Then, if we couple many of these, their excitations can tunnel from one to another, and we get a model that looks pretty much like the kinetic term of the Hamiltonian. On the other hand, if we replace the linear inductances of the circuits by nonlinear ones, in particular Josephson junctions, the oscillators become anharmonic, which ultimately leads to the interacting part of the Bose-Hubbard Hamiltonian. So this Hamiltonian, this model or variations of it, have been extensively studied both theoretically and experimentally, but what we realized in our group is that these modern platforms allow us to extend the model in ways that are impossible in condensed matter systems. For example, using external generators, we can inject excitations by pairs coherently, leading to a term in the Hamiltonian that breaks particle number conservation. And going further, the same transmission lines can be used to engineer dissipation, which can reach a dynamical balance with the Hamiltonian and steer the system into interesting quantum mechanical states. For example, in this recent reference, we introduce a mechanism capable of stabilizing the systems into an unconventional superfluid state with bosons condensed with non-zero momenta, leading to a stripe pattern for the particle number in real space. And even more interestingly, we also show how to create exotic superfluid states with bosons condensed on a closed ring in momentum space, leading to a uniform particle number in real space, but with a non-trivial phase portrait, as you can see here. So these states are predicted to be very important for open problems in condensed matter, such as high TC superconductivity. After this detailed example of driven dissipative Bose-Hubbard models, let me now briefly mention the other main research lines that we work on, all revolving around the big topic of open quantum systems. So we can sort these research areas in three main groups. First, we developed tools of general applicability for situations where conventional methods fail. Then, as I briefly mentioned in the previous slides, in open systems, dissipation, driving, and interactions tend to equilibrate with time, steering the system into a steady state. So we are using this feature to design situations leading to interesting steady states, what is commonly known as dissipative state preparation. Finally, we also work pretty hard on proposals for the experimental implementation of interesting models leading to non-trivial behavior of open systems under realistic conditions. So let me give you a few examples for each of these topics. So regarding methods for open systems, a very challenging situation is when the open system goes through a phase transition of some kind. Traditional techniques tend to fail close to the phase transition, and we have developed methods that can treat the systems even in these challenging situations. So even beyond the phase transition, traditional methods usually fail when there is spontaneous symmetry breaking of a continuous symmetry. For example, as in this system, where the cavity and the injected field in blue are invariant under rotations around the propagation direction, but the field emitted by the system breaks that invariance. So these symmetries can be related to spatial translations, such as in this example, but also to temporal translation, which connects to the topic of time crystals that other people at the Wilczek Quantum Center are working on. And moving forward, traditional techniques for open systems work well when there is a clear separation between the system and the environment, which typically is much bigger and involves an infinite number of degrees of freedom. However, imagine a system made out of several parts, such as this one, where we have two optical cavities, one in purple and one in yellow, that interact through a dielectric material that they are sharing. So sometimes we want to focus on one part and treat the other parts as a kind of environment for the part that we are interested on. Or perhaps we have a situation where the time scales of the evolution of the system and the environment are similar, and we cannot neglect the effects of the system onto the environment. So we have provided techniques for these types of situations. Okay, so on the state preparation side, we have worked on the stabilization of several types of non-trivial states. First, on the generation of states that have reduced quantum fluctuations in some direction of phase space, which have a lot of applications in high-precision metrology, for example, on gravitational wave detectors. So these states are known as squeezed states, and they are intimately related to entangled states, which feature non-trivial quantum correlations between the parts of the system. So, for example, among many optical modes with the non-trivial spatial shapes that I am showing in this picture. So we have also worked on the preparation of cut states in the motion of macroscopic or mesoscopic membranes, which is important in order to test whether quantum mechanics works at the macroscopic scales, or there are corrections to the Schrödinger equation that do not allow quantum coherence to build up for large objects. And still regarding state preparation, we also work on techniques for spatially extended systems leading to the emergence of non-trivial spatial or temporal order. For example, as was the case of the unconventional superfluid states that I presented in detail in the previous slides. So finally, regarding the implementation of interesting models in experimental platforms, we have shown how to engineer clean laser models with superconducting circuits, leading both to standard laser states or even to more complicated quantum mechanical states. So we have also shown how to generate parametric oscillation models in the motion of membranes or other mechanical objects. These models are the simplest open models leading to phase transitions and spontaneous symmetry breaking. And finally, we have designed systems that act as deterministic downconverters, that is, systems that can transform a single photon that arrives to them into an entangled photon pair with 100% probability. So the people who join our group are welcome to contribute to the different ideas that we are pursuing in these areas, or as I mentioned at the beginning, we are always happy to start new areas where we can exploit the expertise that we have gained through working on these open problems. So again, let me thank you very much for your interest in our group. I hope that you got to know us a bit better after this presentation. And please feel free to contact me at any time if you want to know anything else or if you are interested in working with us. See you!